Okay, very good. All right, so let's formally start the session. So again, hello and welcome everyone to the fifth session of the webinar series of Elements of AI Luxembourg. So I'm your host, Dr. Jeremy Dauphin. And the guest speaker of today is actually Professor Martin Theobald, who's also a co-organizer of this series of webinars. You might remember him from the first session of the webinar series. So Professor Martin Theobald is a professor at the University of Luxembourg. He's also the head of the Big Data Research Group. He obtained a PhD in 2006 from the Max Planck Institute of Informatics in Saarbrücken. He was previously also a professor at the University of Antwerp and the University of Ulm. He has served as a program committee member, reviewer, and organizer for more than 100 international conferences, workshops, and journals. Many of which are among the top in the area. And also something notable is that last year he received the award for teaching excellency at the University of Luxembourg. And so today in his talk, he will tell us about current topics and trends in big data analytics. Just a short reminder that we'll have a question and answer session at the end of the talk. Please, Martin, go ahead.
Yes. So everything okay to sound? No, it's a bit disrupted for me. Can you hear me?
Yeah, we can hear you now, yeah.
Yeah, okay, good, great. So thanks for the introduction, Jeremy. It's my pleasure to tell you a little bit more about what we're doing here in terms of research, but also in terms of teaching. So actually what I have here is an excerpt from my big data analytics lecture. So whole lecture in 45 minutes in some sense, but only the highlights, of course. Here for today, which gives you an overview basically of some trends here in the area of big data analytics. So I'm not exactly a professor for artificial intelligence, so big data, I guess, depends really on how you interpret this as well, but I think it's close enough, so I think it's also showing a bit more beyond of actual just what is called artificial intelligence. So I have basically a motivation section and then 3 big data use cases. So how can I switch over here? I can go there. So I'm starting with this platforms map. This is from 451research.com. As a rating agency in the US, they release this kind of platforms map for big data tools and systems, essentially, every once in a while, every couple of years. This is the latest one I could find. Is from 2016. It actually shows all kinds of big data systems that you can find out there. It's actually divided into 3 zones. Like the relational zone, the non-relational zone, and then some grid cache zones here basically. But especially in the relational zone, you find like lots of like classical database vendors, so Oracle, Microsoft, SQL Server, also SAP HANA somewhere here in the middle, if you're looking for this. So these are systems essentially that speak SQL and have been adopted to big data platforms in the sense of making them distributed, right? And then the non-relational zone, these are less classical, more modern tools. They're not really SQL systems, not SQL only. So that's the area that we call no SQL. No SQL basically meaning not only SQL or no SQL at all. So you have to program against them often. But these are also the platforms that we're more and more using now in the lectures and to basically build up these use cases and everything, all these kinds of things. So on the left-hand side, there's things like Apache Hadoop, most notably, if you heard of this, Apache Spark, using MapReduce and these kinds of things, and MongoDB and all of these areas. So basically had it here, yes, as a small animation. You know, no SQL here on the left-hand side. The less conventional platforms, SQL, the more classical platforms adopted to distributed computations here as well. Scalability is very important, running this on clusters. And then in the most extreme case here, you have specialized engines that have been basically been specifically adapted to HPC architectures as well, high performance computing. So what is big data here? You see, like in the real world, I think nobody knows really what exactly big data is. It's not a very precise term, but like in the real world, I think big is very subjective and inflationary. So I still remember me buying like my first 1 terabyte hard disk. I was very proud of that about 10 years ago. And then 1 terabyte obviously was very big for me at the time. Today you can find like a 1 terabyte hard disk at your favorite supermarket almost for about 25 euros per terabyte. So you typically buy 4 terabytes for 100 euros or so. But what we mean with a big data problem, so if you're tackling issues, things that you want to compute over big data, it might mean that you cannot store simply all the data in a single machine anymore. And we typically speak of commodity machines, so-called commodity machines, which are typically not the high-end servers. So you take more or less mid-sized servers, the actual servers, not desktops, but servers of medium size, so few terabytes hard disk, few gigabytes, maybe 32, maybe 64 gigabytes of RAM. And then you try to do something, and you try to scale out your computational problems over multiple of these machines to basically scale out these things, if the algorithms that you have permit for this, right? That might also mean that queries cannot be processed by looking up individual data items or using indexes as you have it basically in a nice database architecture or something like this. Even sequential scans over the data may be too slow. So if you scan all the data, if you have a petabyte of data and you want to just find some average salary of some employees or something like this, if you would read the entire petabyte or something like this out of this, would be too expensive. You might want to actually sample over the data and these kinds of things, right? Or you have more analytical queries rather than updates. So you hardly have updates over individual data items as you have in a classical data warehouse or transaction-based system like a database. Yeah? And then the last point is what I want to highlight more is basically if you have an algorithm or setup that works well on a single machine on X bytes of the data, I don't know, 100 gigabytes or so, and you just take a little bit more data, in the end, everything might break, right? And then nothing works anymore on that machine, and you have to think about how to scale it out, how to use multiple machines. Sorry about my voice, I'm just coming from another lecture, actually. So here's a first big data showcase that I like to show also for my lectures in the beginning, basically to motivate for what might be a big data problem. So here the showcase is to calculate the world's population's median age grouped by gender and country. There's actually a paper by Adam Jacobs from like 10 years ago, a bit more than 10 years, meanwhile 12 years maybe. This is basically when this whole big data wave started in some sense, right? So what he was doing is to basically simulate the world population in a large file using 6.75 billion records. It's roughly the population, I would say, of that time, storing one row, one entry per simulated human on Earth. Of course, it's a synthetic data set. It's not real data, right? Using 16 bytes per such entry, representing one person maybe in the world. And if you do this, if you take these 6.7 billion something times 16 gigabytes, you get 100 gigabyte as a file. Not too large, can be stored on almost every hard disk nowadays, right? And then you basically simulate different characteristics of your population. So you have basically one bit out of these 16 bytes that represents the gender of the person. So binary, at that time still, binary gender information. You can use one bit for male or female. Nowadays, you might need more, right? So in Germany, you also need diverse also, these kinds of things. So you need more than one bit meanwhile. Nevertheless, you have basically also like values for the countries. So I think there are about 190 countries in the world. 256 is more than enough using 8 bits. So that's per entry, one row in this format. And then 7 bits for the age. So essentially simulating ages between the age of 1 and 128, which should also be enough in practice, right? So what you get is actually a matrix, if you aggregate this, to find this median age per gender and country that contains only 2 times 128 times 256 distinct entries. So it's a very compact data structure. So if you store this as a matrix using integers, like a 3-dimensional array or something like this, you basically have possibly something like 65,000 times 4 bytes, like 250 kilobytes only that you need to aggregate all the values from that 100 gigabyte file into the very compact data structure, and you can evaluate your query. So it's actually a very simple computational task. It's similar to computing averages anyway, if you don't know what the median is. It's actually perfectly linear as an algorithm if you think about it. So next slide would contain like the summary of that. So like the illustration. So you basically scan through the file, it's the left-hand block. And on the right hand, you actually compute these medians by loop over all the genders, the sex essentially here, then the countries with the given range, the ages and so on. You do this once, you basically compute like the middle point, and then you essentially have it, you know, the median. The median is the point at which the distribution is split into 2 equal halves essentially. So if you split this, implement this basically in an own custom program, well-tuned C++ implementation would take 15 minutes if you store the 100 gigabyte file on a hard disk. So the limitation here is mostly reading the data from the hard disk, which usually has 100 megabyte per second, something like this in terms of read rates, old rotating hard disks nowadays, right? In those days, nowadays, you have SSDs or so, which are of course a bit faster. If you do this in main memory, so of course you can also have a computer with 100 gigabyte main memory, then it would actually take less than a minute. So it's not really that expensive. And then let's see what Postgres would be doing. So as a comparison, he implemented this basically as a similar query in Postgres. This is like the SQL behind this. It's not exactly the same. Postgres doesn't have the median built in, so we're using averages and these kinds of things. If you look at this and measure the runtime of Postgres over an increasing number of the data, you see basically the difference in practice, what happens here basically. So you have basically the blue dot on this curve for 10 to the 3, 10 to the 4, 10 to the 5, 10 to up to 10 to the 9, which is the billions records basically here, and versus the runtime, and that's on the log-log scale. So on this log-log scale, all plots, all polynomial plots that you can have from linear, that's the orange one, to the yellow one, which is n log n, which is for sorting, up to the quadratic curve would be perfectly linear lines. And what we see here is that Postgres is actually starting very well. So it's actually within a linear performance here that we would expect, so performing very, very well up to a certain amount of records. And then even gets a bit better, probably due to interpolation in the upper range. Unfortunately, I cannot show here, but if you go to the 10 to the 7, 10 to the 8 on the x-axis and beyond, basically, you see that everything breaks down. You're becoming parallel to the quadratic runtime, right, which is extremely bad. So Postgres probably starts very smart here, does something in main memory as we would expect it, and then at some point, like switches into panic mode, swaps all the data onto some intermediate storage on hard disk, and then basically degrades to very bad performance. So quadratic is something you don't want to do on big data sets at all. It's not generally feasible, right? So the entire, I think I have it here, run would then take 24 hours. So that's basically what I mean with the big data problem, right? So you have something that is fairly easy to solve usually, would expect no major problems. It works very well on a certain amount of the data. You just take a little bit of data more, you add something, everything breaks down basically. Yeah, and that's, I think, a nice use case, how to look at these things. Yeah. So what is big data, or the big data area? Here is just a few numbers that I found on the web basically here for like units or sizes of different known companies, let's say, in terms of what they might be storing. Numbers might be slightly outdated, might actually be larger. Meanwhile, of course, you see the big US companies here leading essentially. So one benchmark here is basically how much data they have overall in their data centers, but also how much data they process per day, right? This is also another very marketable factor. And you see on the blue box, basically the units, right? The orders, so from terabytes to petabytes to exabytes, you always go by 3 orders of magnitude, essentially 3 powers of 10, something like this, right? You can also look below here, that's the largest single data center, the stuff from Google here, the 15 exabytes, it's the upper figure here, is distributed. It's not a single data center, but the largest single data center that I could find basically is this Utah data center here. That's actually run by the US intelligence agencies, has been built fairly recently. You can look up the Wikipedia article, link is going to Wikipedia. And that is supposed to be storing about 1 terabyte per human on Earth, right? And that's, of course, also like a nice benchmark. So that has, of course, many controversial issues as well, many privacy, many security issues, and so on. I think Luis Lever in the last lecture gave you a bit of an idea about this, what you can do with mouse clicks and mouse movements and these kinds of things. And here's like a nice figure. So what we need is scalability here. You want to scale out. So if everything breaks on a single machine, maybe hopefully we can go to multiple machines, right? And then distribute our computations. So 2 important terms here are scale up versus scale out. So scale up is on the left-hand side. It's obviously limited here. If you stack up a single server, a single machine more and more, you end up at some point with some architecture like this. This is an actual figure of the first Google server that they had at Stanford at some point, right? I think Google was established or founded 1998 or so a bit more than 20 years ago, so not that long ago actually. And then of course they went quickly to completely different architectures. And what you actually want is what we call scale out. That's the other technical term here. Scale out is basically this distributed computing, going to large amounts of machines, mostly commodity machines, and then doing things in parallel. And then you get these typical pictures here, these architectures with the huge halls, which are full of racks, right? And then racks have so many servers inside, and that's what we call a data center here, basically, then as well, right? So here's another data center picture and these kinds of things. So I also like showing this one here. That's a little less known. Anybody heard about that maybe? It's a so-called Sun modular data center. I also like showing that in the beginning of my lectures typically. So that's, I think, a very nice idea. That's something that Sun Microsystems offered at some point, maybe 15 years ago. You could actually order an entire shipping container, regular, shipping container, I don't know, 12 meters long, 2-something meters high, and so on, that fits on a ship or on a truck. That's full of these blade servers. So it's full of racks, and then you can basically order this as one unit, and then you have your own data center in your backyard, so right, and you could deploy this. You only need to plug in power and cooling. Cooling is very important then as well. Right? That's a nice idea, but it's out there. It doesn't exist anymore, right? But it was really like a product they offered at some point. And meanwhile, Sun doesn't even exist as a company anymore. It has been bought by Google, Oracle, sorry. And here's a nice link. You can also look at this. Unfortunately, I cannot click on the link here, but that's like a street view into the Google Lenoir data center in North Carolina. So they offer basically something like a street view inside the hall, so you can actually very nicely walk through the hall and the data center, see the racks and everything like this, right? That's also a nice feature. And I found this link when they made it public in a /Q article also about 10 years ago already. So also nice anecdote. Of course, there are many different platforms meanwhile. So most notable, you have like Amazon as well. You have Azure, it's a Microsoft platform essentially here. There are different links that you can follow if you want. So there's a nice Wikipedia article just about the different cloud platforms, openly or publicly accessible cloud platforms that are available in the world, that currently lists already more than 50 such platforms. So that's quite a lot as well. Actually, university has a very nice own data center architecture. So we have several floors full of racks. That's quite amazing for university equipment as well. That is managed by a colleague of mine, Pascal Bouvy, basically. Then what is Spark here? I mentioned basically these newer platforms, these big data platforms that are not so much coming from SQL, from databases, but have been specifically developed for these distributed computations, for these scaling out architectures in some sense. So Spark has initially been a prototype that was developed as a PhD thesis actually in Berkeley, University of California in Berkeley. The PhD student from that time is now a professor in Stanford already and these kinds of things, but it was really like one thesis, one particular topic that has been developed and then really started taking off a lot and has now meanwhile been involved as a major big data platform that is really worldwide used for all kinds of analytical tasks here. So that's like a highlight here from 14 when they basically became open source as well. So it's basically a unified platform for collecting, loading, storing, exploring, analyzing data, and then also having a lot of extensions for machine learning, graph analytics, and these kinds of things here, basically as well. This is the actual platform we're using also for the lectures at the university, for example, here. So it's basically supporting all kinds of language plugins. So the actual core implementation is in Java. So you can deploy this. It's basically distributed if you install it on multiple machines, but it's really Java processes that talk to each other. But it then has many language front ends, for example, for statistical computations in R. For SQL, has a very nice SQL support meanwhile. Python, Scala is a very nice functional programming language, and then of course also Java itself here as an API, as an actual programming front end that users can then use to implement their own algorithms and data structures. And then top-end components, meanwhile, also include many streaming extensions, machine learning extensions, and these kinds of things as well. I'm actually showing you a few use cases using the machine learning libraries here in Spark then in the following part. Here's a typical example. You don't need to read this at all. It's just to illustrate this. So many of these inventions here, if you think of Hadoop, which is in some sense the predecessor of Spark, come from web crawling. So they have been implemented in order to process large amounts of web pages that have been extracted by search engines and then basically have to be indexed and processed and analyzed in various ways. And that's where this computational paradigm, these distributed computations come from. So word counting is the most basic such analysis that you can do for web pages. You just extract basically all words occurring on all web pages on the world in a large web crawl, and then you analyze the frequencies. That's essentially word counting. And here would be a Java implementation of this word counting examples with a simple tokenizer, taking so and so many pages as input, running them in parallel. So you can parse the pages in parallel, you can extract the keywords in parallel, and then aggregate these frequencies also in parallel, basically. In Java, that's like a Java excerpt, an example here. And then if you do this in Scala, if anybody used Scala here, it's a functional programming language that is embedded in some sense into Java. It's like 3 lines of code, right? So if you have this beautiful file here, stored HDFS is the Hadoop distributed file system for example here, entire internet.txt, if you happen to have that file at hand, it's probably large, then you need one more line of code to basically extract these pages. So it's a bunch of transformations operations to extract the terms, to basically add a counter to them, and then to reduce it into the common word counts, and you can store it, and you basically have your analysis, right? And that's the style of building entire data flow programs, more complex algorithms, even machine learning things on top of these distributed data structures. Of course, there's many vendors involved in that, so all of the major companies, let's say, coming from databases, but also more recent companies here are involved in these kinds of things now, using Spark, for example. So then I have a few more minutes here, 20 more minutes, I think 25 more minutes for some use cases. So first use case is actually going now into the machine learning libraries in Spark. What we can do is to try to build a simple recommendation or recommender system. It's a form of collaborative filtering as well. So the idea is that you basically exploit the ratings that users provide for particular items like movies or songs that you like or something like this, like a Netflix, Spotify. To exploit these ratings from the users to recommend new items to other users that might have similar tastes. You can basically compare many millions of users then with their different music tastes, and in case there's a similar user that has listened to most of the artists that the other users like, then you might actually recommend also such an artist to that user, as an example. That's what we call a recommender system here. Typical data science workflow, so essentially we want to build something like a machine learning model, doesn't work typically in one shot. So you need multiple iterations over this. Normally this is animated, didn't work out with the PDF, but usually you start basically with loading the raw input data. Right? So you have to get a hand on your data and basically start manually exploring as much as this is possible the data files themselves, if it works, if it's not just like some weird binary format, but maybe some CSV or TSV format that you can actually at least visually inspect and get an idea of the data. Next thing, that's now number 3 here, basically would be to prepare and transform the raw data into a format that the machine learning technique, the libraries actually understand. And for that, you need to basically know the APIs, basically, and know what the advantages or disadvantages of the different feature functions that you can have are, basically, in order to bring the data into a good shape that the machine learning libraries then actually understand. So even though the learning part might be optimized, the human engineering behind this, behind the feature functions and all these kinds of things here is still very important. So even if Luis Lever told you that deep learning removes all of this, it's not always completely true. If you don't understand the data at all, you hardly have a chance to get good results as a data engineer or data scientist, right? And then once you have the initial model, of course, you can do some predictions, you see some initial results, position and recall, these kinds of things. And then you can essentially improve the model, improve the hyperparameters, tune this. So you need more iterations, you start loading the data again, and then you're basically in this circle here. So it usually takes a lot of human engineering still and basic understanding of the data that you're actually working with. So this is why this example, I think, is nice as an illustration here. So we have a basic technique, machine learning technique. This is in this case called ALS, alternating least squares. It's a particular form of a matrix factorization, decomposition, basically. But we apply it to data that we have from such a large, let's say, Spotify, Amazon, Netflix setting, where we have ratings about different movies or different artists here. I think this is from what we used here. It's from Audio Scobbler. It's actually open, so we can actually play with the data and then see really what's going on behind. So just in a nutshell, it's a bit of some math formulas, but very short here. So what we want is basically a decomposition of a large matrix. So let's say the users could be the rows representing the rows in this matrix. It's 2-dimensional. And the artists, or the song that we want to recommend, are the columns. Right, actually, I can show that. I think it's on the next slide. So here you see an idea here. So A could be of this shape. So we have 3 users for 3 rows and 4 artists, right? Now the idea is that we're looking basically for a decomposition of this matrix A into 2 smaller, typically smaller matrices, X and YT just for the notation here, such that when we multiply them back together, we get an approximation of A. Yeah? And under certain conditions, depends on the sparseness, in particular on the ranks of A, if we decompose this into a projection that has less dimensions than the original matrix, we get a compressing effect. So if you basically have a rank A or a matrix A that has a rank of 2 here in this case, and we use a decomposition that is basically 3 by 2 and 2 by 4, we have no compression yet, so we just get an approximation. But it comes to magic, basically. If you do the same decomposition on a matrix that has a high rank, a full rank, as it is typically the case for a recommender system, so many users having slightly different tastes, no user is really resembling the same other user exactly, then you get a very high rank matrix. And when you then basically do the same decomposition, you need a particular algorithm for that, you don't want to do that manually, of course, and you get a very nice compensating effect. So if you look at the below A matrix, you see basically that the first user has not listened to the third artist, for example. There are lots of zeros for the first row, right? But by comparing that user maybe to the third user, the third row, who has also a bunch of zeros or so, you can see that there are some compensating effects. So the zeros that initially were there, right, become filled. And that we can use for the recommendations. That's the main idea. So the zeros, by this lossy, by this like approximate decomposition, become recommendations for the users, right? So if you basically see this here, for the first user, the row 5, 7 becomes filled with 6.4, 5.8 as well, and that's basically the order of the artists to recommend them. So the third artist would be recommended, the fourth artist, and so on. Of course, it happens for like millions of users and millions of ratings. What happens behind this is a certain maximization issue, so minimizing some kind of a loss function, and a particular algorithm here that's called alternating least squares. I really don't want to go into this. You get this beautiful expression here in terms of matrix operations that you can do. But what you really want is to make that scalable. Also in Spark, you can basically distribute the matrices. So matrix multiplications are basically always row versus column operations. So you can distribute the matrix in various ways and then basically also parallelize these computations. Anyway, you don't solve it exactly. This ALS is clearly an approximation technique. And this is an initial evaluation here for this particular ALS setting in comparison to MATLAB. If you heard of that, for example, it's a centralized system. Mahout is a Hadoop-based, is also distributed, data mining library and other ones. GraphLab is a highly optimized C++ library for various data mining tasks. So Spark here is actually faster than most of the systems except GraphLab in this case, which is really highly tuned and specialized, right? And that's on a data set from Netflix from about 10 years ago, which was scaled up here as well, which contained already more than 100 million such individual ratings, for example. So that's one use case. So I think the use cases are quite fast otherwise. So the second one I have is related. It's also a matrix operation, matrix decomposition. So algebraic stuff, so a little bit of data mining here as well for text analysis. So it's called latent semantic analysis or latent semantic indexing. Essentially, the idea here is basically that you have documents containing terms. If you translate this to a matrix, it's usually very sparse because there are relatively few terms per document, and most documents don't, of course, contain all the terms. So that means very large, very sparse matrices. And then when you represent this, decompose this, you might actually want to find similarities between similar words that have no string similarity, but represent similar concepts, hence latent semantic concepts or analysis here. And also similar documents that basically can be clustered this way. So if a user basically sees these 3 documents, like Jaguar as an animal or cat, Jaguar with a car brand, or then Jaguar luxury vehicle, the user would type the query car brand. The best match based on strings is of course the second one, car brand, right? But the system might identify the car brand is similar to basically luxury vehicle or vehicle and also return in the third document in some sense. So these become related. And you can actually find things that you couldn't find before. Well, it's like a document clustering or term-based clustering as well. And then maybe last, in some sense, since it's also kind of similar, the animal versus the cat. So this is a different kind of decomposition. Also, I don't really need to go into details here. It's called singular value decomposition in linear algebra, basically. So you find 3 such decomposed matrices, where the middle matrix is a small one containing all the singular values here over the matrix A here being decomposed. So M is the number of terms, N is the number of documents here typically. And also here, the trick is to basically reduce the dimensionality of this decomposition. So instead of computing a full decomposition, which is an exact representation of the original matrix A, we also use a reduced decomposition by using only k dimensions in the middle matrix. Here it's the center, S k by k basically, that contains the k largest such singular values that in some sense represent these k largest or dominant latent topics that are in some sense hidden in these documents. Yeah? So that's a default math procedure to basically apply this. Could look like this here. So we have the full decomposition here. We have, I think, 5 rows, 5 columns here as input. You would get something like this if you have a good math tool that can do it automatically for you. But by cutting off basically the k largest singular values in the upper corner here of the middle matrix, and correspondingly cutting off the other matrices by the k dimensions that we want, you get a lossy, but again compensating representation of the entire system here, right, into smaller matrices. And then we can actually use this representation. The first one, the left, the U matrix, would basically represent the terms. The right-hand matrix would represent the documents mapped into this latent space here. If we compute basically similarities for words, we could get something like this here in the end. Of course, it's ideal outcome here that, for example, the first word might be representing Jaguar, would be highest similarity if your cosine is typically a cosine similarity measure for vectors represented by as rows in these matrices then, basically being mapped to the car, which you didn't know before. So now car and Jaguar become similar. Of course, Jaguar to itself is most similar, but car and Jaguar become the next most similar pair, and then maybe after that, Jaguar and the cat possibly, or something like this, right? Last topic, so last use case, I have basically something for the financial analysts among you. I'm not sure if you're familiar with different statistics there, like the VAR. It's possibly a bit full on the slides here, but value at risk, VAR, is a typical statistics used in finance to measure like the risk of a certain investment, of a portfolio of stocks, so these kinds of things. Also, this works in Spark, so completely different setting now, no matrices anymore, but still using Spark here as our basic platform. Right? So you could also see the code if you're interested for these implementations. So the VAR itself is defined as the first 5% quantile of the worst returns of a portfolio that you could have under different market conditions. So you can have a portfolio of different stocks, let's say, that you have bought. You have market conditions like, like different stock indices, major indices, gold prices going down, unemployment rates going down, corona rates going up or down, these kinds of things, they all impact the market, of course, you see that. And we're basically measuring the returns of these stocks here over a given fixed period of time, let's say 2 weeks or so. It's part of the VAR estimation, it's a parameter of the VAR, how long we measure these returns, basically. So we see the stock returns, we see the factor returns, and then we learn a linear regression model, essentially. It's yet another such data mining, or if you wish, also machine learning technique that basically learns correlations between the factors, which are the observed variables, and the returns, which are the predicted variables. Yeah? And then we can basically simulate the VAR by applying this linear regression model, feeding a lot of samples into that, and then basically taking the first 5% quantile of the worst returns, which is a measurement for the risk that we might have for our portfolio. So it looks like this typical figure here from some stocks. So essentially you fix a period of time, that would be the low bottom line here. Typically we take 2-week intervals here. You can take longer, shorter intervals to see basically how safe your investment could be over a longer time versus a shorter time as well. It's basically typically this kind of time series format that you need here, time series data that has the target value, like the return or say the stock price that you invested in, with the timestamps of the measurements that you have. And then you can basically call a return or define a return over the opening versus the closing price and vice versa. So here's like typical return. So if you focus on the closing prices, if you say you have gained something, if the closing price is higher than the opening price after 2 weeks or so, you can define a return here as a closing price for a given stock I here, minus the opening price over the closing prices. So it's like a percentage, but can certainly also be negative. So you can actually lose something. It's not really a percentage value, right? So it's a normalized value otherwise. And then we can combine this with different factors. So market factors here we used is, for example, major stock indices like S&P or general domestic product information. Gold price could be helpful and so on. So you basically have all of this data stored in different files, which can be read nicely into Spark, and then you essentially feed it into such a machine learning formula. And here's an example for how the return could look like if you have this time series data. I think this is from the Google Finance format. It's no longer available as a service, but you can take Yahoo or whatever, Yahoo Finance or your favorite stock provider if you wish. Return here would be positive, so like something 0.02, so you gain something after 1 week. I think this was over Christmas 2013 from that data file basically. So we're using open data mostly. And then this is also a formula. I can briefly mention what it is. It's a typical linear regression model. So the input is basically the factors that influence stock price or return of a stock price. So the FJs are different factors, like these stock exchange prices, S&P, general domestic product, or whatever. These are all different factors that impact the return of a stock in a certain way. And we can actually learn that. If we have enough training data, then we can feed a lot of stock observations and see how the respective return over that is. And the formula here is like the simplest such machine learning formula that you can have for linear regression. It's really just a linear equation system that you have for each such return, right? So if the stock price is going up, or the general domestic product is going up, then the stock price might also increase. So you see basically these dependencies here by combining the different factors that you have onto your target portfolio in a linear manner, by summing them up. And you need to align the data and these kinds of things. So if you basically have the stock returns, this is the eyes here of the stocks you might be interested in, just an example, no recommendation at all. And the factors that might impact them, you might actually also want to handle something like correlations often. So if you assume that the factors all behave independently and each impact the stocks that you have in an independent manner, that's an oversimplified model often. So you want to actually model something like correlations. So the weights that you have, the pairwise weights, are the weights from the factors to the stocks that impact them according to the formula. But also between the factors, you have some dependencies, right? And you can refine the model, the regular linear regression model, then by modeling something like, or inventing something like correlations, measuring also correlations among these factors then. And the entire procedure here goes then in 2 main steps. It's a learning phase, so it's an actual machine learning technique. It's not just like a mining technique, but it actually learns parameters for this linear regression model. If you remember the formula, if not, it's also not a problem here. It's the CI and the WIJ parameters basically that impact this, that tell you how large factor impacts a given stock price. So we take the training data, the observed values of the factors and the stocks from the past, learn the parameters of this model, that's the learning part, and then we can make prediction by running different kinds of new stocks, generating new stocks, simulating this, and generating new returns, and then basically finding what are the 5% worst returns to have the VAR. And that's this procedure, this continued sampling over different kinds of returns, it's called Monte Carlo sampling typically. It's a very broad class of sampling, Monte Carlo, of course. Could look like this here. So you have basically pairwise correlations. It's a so-called multivariate normal distribution. So you make it a bit smarter than just saying, okay, everything is independent by using such a correlation way of modeling correlations. So you can see that certain combinations of input values, X and Y, are simply more likely than other combinations. And that makes the thing less going away from this independence assumption that you would have otherwise. So if you basically have a high peak in the middle here, in this nice bell shape, then you would more likely take values in the range of 50 and 50 for X and Y. It could be your factors, for example, rather than combining a very low value with a very high value, which would probably be unreasonable in reality. And these distributions, you can also learn from the data. You basically have the parameters of the distribution, covariances, and so on that you can learn from the data. And then for the files that we had here was basically three stocks, or yeah, three stocks that we had to measure the returns. That was our portfolio essentially here. And then three effector files from, I think, an observation of about 3 years or so. Yeah, 1st of January 2000 to end of December 2013. And altogether, that's not so much data. That's about 20,000 lines of CSV data for the input data, for all the time series that you get for the three stocks and the three factors here, three shares. So it's actually quite fast to learn that. So you can plot basically the returns over that observed data, over the past data. You see that, if I go back here, that between the two bonds here, the two ETFs and the gold shares, there's a big difference. So gold is in the middle. Gold is by far the most reliable one, has the least spread. So also the least gain, but also the least likely to lose something, at least at that time, right? It has been changing a little bit a few years ago with Corona, I think, right? People more invested into gold recently. But at that time, everything was centered nicely around 0, and then like you see the differences between the different returns here. If you're running this Monte Carlo sampling, then in Spark, you can do a lot of samples. You can literally run hundreds of millions of samples in a distributed manner, also in parallel over that. So you can nicely distribute the sampling procedure, and you would run everything to measure the returns according to our linear regression model that we learned before. And then you would get something like this for the returns of your actual portfolio. That's the output essentially. There's also like a nice bell shape, more or less centered around the mean. I think the actual mean is a bit positive here, so it was not such a bad guess at that time to invest in these stocks. And we can basically then measure the VAR. This is our target statistic here as this 5% quantile. And that's basically here, I think it's centered at minus 0.026 or so. So if you would invest like 1 million into these three stocks, then under the 5% worst conditions that could possibly occur, you would lose 26,000 something. I think that's what you conclude from this VAR here. That's the 5% quantile. So this is very cut up after the 5% worst observations. Yeah, that's my 3 use cases. I think I'm pretty good on time actually. So final part here from the lecture. If you're interested in this, highly recommended literature on big data platforms, Hadoop, Spark, and then the use cases are actually taken from the third book here, Advanced Analytics in Spark. So that's really nice. The first one is very large. It's like 12 years old, I think, or so, first edition at least, has more than 600 pages or so. But anyway, this is like the holy Bible in distributed computing, at least for these open platforms. And then the use cases are taken from the last book. I think it's also very nice to read through. This is really written by data scientists from different companies. That will be the book. And finally, last slide here is my word cloud here that I compiled from the lecture. That's from our big data lecture. It's concurrently being taught in the master now in Luxembourg. So I actually took the PDF version of all the slides, you know, and then extracted the text, and that these were the words, the terms that came out most. All right. Big data analytics, of course, occurs in the bottom line of every slide. That's why it comes out so close. It worked out nicely. Okay, this is all from my side.
Okay, thank you very much for the presentation. It was very nice. We can move to the question and answer session. Okay, first question already.
Duplicates. Oh, it depends on your application. There are many forms of duplicates. If you have images or text documents which are duplicates, there's a huge amount of fingerprinting techniques. So exact duplicates are simple, if you mean that. If you have 2 exact images, you compute a checksum, like an MD5 code. If you know about that, that's a fairly large checksum, 128 bits or more sometimes. And you compare the checksums and you have the duplicates. It's like hashing. That's very fast. What is more complicated are near duplicates. So if you have small variations, you know, it's like a slight form of plagiarism, maybe in text documents, or some different angles of the same motif, of the same picture, you know, that's much harder to find. So then you need to extract features then often and compare the features. But exact duplicates, if that's what the question is about, are quite easy to find typically in large data sets. It's a linear path. It's like hashing essentially. Near duplicates could become quadratic. It's quite expensive if you do this in an exhaustive search manner. I'm not sure if that was the question. It's actually otherwise very technical if you want to answer in more detail, or you need a more detailed answer. Well, so for like the research that we do, honestly, I try to stay with open data sets, which is not in the petabyte scale typically. So if we go for like Wikipedia articles for text analysis or open image data sets or so, then we're basically safe, but it's not going to be in the order of petabytes. Always for specific projects, we might work with companies that actually have non-disclosed data sets, but that's always a lot of issues. It's complicated. I try to avoid that personally, to be honest, to work with non-open data sets. If you want, yes, you can. Easiest way is to follow the book, the third book. It has a GitHub link. So you just search for the book on the GitHub that has the exact version of the code, also with pointers to the data sets. And then, of course, we do other things. We modify this in different ways. But if you just are interested in the implementation, let's say, of this var function, for example, you could take the pointer from the book, this advanced analytics in Spark, for example. It's very well documented.
Okay, that's quite nice. Yeah, maybe we can also put the links, we can post them on Reddit afterwards. Make it easier. I think also you had quite a lot of links in the presentation, which unfortunately we we could not make them interactive.
The links, I think they are fairly safe to click on. They're mostly Wikipedia or something other as well, openly available with a few more pointers.
Then I can post, make a compilation of all of them to put on Reddit.
Yeah, but I think the PDF file, if you upload to PDF, it contains the links.
I will also, yeah, I'll do that as well.
No, that's fine. Oh, there's so many words and names for things. I would say if you're a database person, then you prefer maybe the term data engineer. It's a more classical thing. If you're a data scientist, maybe that includes more so the math people, you know, AI people are going into data science nowadays as well, machine learning. It's really a matter of taste of how you want to call yourself or so, but I don't see such a big difference. Anyway, all of these are so big fields, like data engineering, data science, artificial intelligence, they have large overlap, and nobody can really tell you what the difference is. I don't want to make any detailed statements there, what the difference is. There is none that you could define. It really depends in the end on what you want to do with the data and where you are settled in your environment. There is actually a shift in the methodology, maybe. That is what makes a data scientist. So in classical statistical applications, people basically started with modeling things, with a nice model. For example, the multivariate Gaussian here, you assume that your data adheres to that particular model and you find the parameters of the model, right? And then it has to fit somehow and makes predictions with some accuracy, and you measure this and you're happy, basically. But nowadays, people go the other way around, and that makes maybe a data engineer, both a data engineer and a data scientist, because you actually start with the data, and then you either pick a model that you think is suitable to the data, but you do not start with the model in the first place, or you go actually all the way and you do deep learning and these kinds of things, and you don't care about modeling at all anymore. You just basically run your deep learning machinery over it and would extract something meaningful, hopefully, then out of the data as well. But deep learning needs a lot of data. The modeling-based approach typically doesn't need so much data. Yeah, and I think that's a much better distinction if you're data-driven or if you are basically more classical model-driven person. It's more accurate. Yeah, as I said, I don't think it's a confusion. It's more or less synonymous. It's the same thing, just slightly different names. Of course, if you work with data, many engineering things are important. You need to know how to store the data, how you can run something on a cluster, how to just deploy things on the cluster, which kinds of tools are suitable, and so on. But I think conceptually, all of this belongs together in some sense. Right? Oh, calculations based on the final exam. No, don't worry. There's no formulas that you need from my slides or any other slides of the webinar for the final exam. No,
yes, the final exam will be multiple choice questions, so you will always have just to choose between 4 possible answers.
Yes, and they are completely based on the online course, not on the webinars.
Exactly. Yeah, so any of the topics covered by the guest speakers will not be included in the exam, unless it's also covered in the course, of course. We'll also give more details about the final exam quite soon, because it's getting a bit closer.
Yeah, I think it opens in 2 weeks. So after the Easter break, or after Easter, actually, after the Easter holidays already, but it stays open for at least 2 weeks. And I think you have 7 attempts, so that's quite self-organized, and you can basically log in whenever you want, whenever you have time. When you start an attempt, I think you have 2 hours, and you have to finish your attempt within these 2 hours, and then we'll close. But we will set it such that everybody has at least 3 attempts, and a certain percentage of the questions have to be answered correctly within each attempt. But it will not be a difficult exam.
Exactly. So normally, if you pass already all the exercises of the online course, then it should be fine. Okay. I think that's all the questions from the audience. I mean, of course, feel free to put some more questions. But maybe
any other questions on the course or so?
If you have any administrative questions, also feel free. We can answer them as well. But I'm a bit wondering, so a bit of my personal questions, since we have some time.
Switching off mine.
So, do you think? Martin, are you still there?
Yes, I'm there. I just thought you wanted to say something, so I didn't want to.
Oh, I have a question for you, actually.
Oh, okay.
So I'm wondering if you think. So I mean, we didn't really have this field of big data. So some years ago, when our artificial intelligence and I mean computer science in general was developed, so it came a bit afterwards as we started to collect more data and have these like also physical limitations. So do you think we also have still have a need for this kind of issues in the future, as we are able to store more and more information and do more and more on let's say single machines?
You mean big data as a field?
As a field, or is it going to go to very big data at some point, or?
Yeah, well, you see, it's also what I meant about data science versus data engineering. So it's just such a broad field, such a broad area. Everybody can basically do what he or she thinks is best for the given purpose or application or so. So I'm personally coming from databases. Maybe you got that from the talk or so. I started looking into these distributed architectures maybe 10 years ago, also in the context of teaching that I did different universities, and it was also very well perceived quickly. So people just became more interested in that than in the classical databases, including myself, of course, because I think it's just a lot of interesting things you can do. And the current way data is produced simply doesn't adhere to the classical database approach so much anymore, because the data is not clean, it's not in a nice schema, it's not normalized, so all the employee addresses are in one table and all the other data is in other tables or whatever. So that is, I think, a trend that comes more and more, and you constantly produce more data. But what exactly big data then is, I told you in the beginning, nobody knows exactly, I think, right?
Right, yes.
I think these issues, they will come up more and in different flavors, of course, and we constantly have to adapt to them, I think. That's the main takeaway message. You always have to do something that is interesting.
Yes, for sure.
Well, blockchain, yes, of course, you can consider as big data if you take all the blockchains in the world together or so. But the question is what you can do with it, how you can analyze it. Right? So if you want to compare which coins have been created where and when, then it's an analytical task. But yeah, I don't know what comes out of it. For blockchains, I think the encryption is more the critical part, and the encoding and the efficient creation. Otherwise, we're burning too much energy on the blockchain creation. Well, yeah, so the data, so again, we try to use open data. I'm using in that case the data set suggested by the book, which is from Audio Scobbler. That was an open platform, or a platform that basically, I think it doesn't exist anymore, but the data has been opened or made openly available. And that's actually user ratings, yes. But there are other things like which are not publicly available, like Netflix ratings or so. Netflix had a nice challenge already more than 10 years ago, the Netflix prize that was kind of popular and famous in the community. So you could win $1 million if you would improve the ratings generated by Netflix by so and so many percent. And then the winning team, so that was a big challenge worldwide, the winning team, I think, had more than 50 such albums as the ones that I just presented, combined together into one prediction. And they actually won the prize and the money in turn. But yeah, the main issue also for me as a professor is to find good data sets that have interesting properties that allow us to try out the algorithms and everything, that are actually publicly openly available and that don't disclose any personal data. Also the GDPR and so on, that's all obstacles that we have to consider then, right? So there's not so much really extremely large data that is then open on the web, for example. There are many open data sets, like also public government data that is published now in open policies. There's open linked data, semantic data that is quite large. Text data, like Wikipedia-like data, crawls, which are openly available. They allow for many things as well, but yeah, disclosed data is a bit difficult always. Right? So you never get anything from Google, for example. We had a project with Google, but they would never disclose the data. Also from the legal aspect, simply very difficult. Yeah, that was the question.
There's a new question here about the energy consumption of big data processing.
Yeah. Is that?
Do you see the question? So
no, I don't see it. I think the question of the big data processing. No, it is actually. What percent of the global human energy consumption is used for big data processing? I do not know that. I do not, first of all, know what big data processing would be different from normal processing, and then I don't know the percentage. It's impossible to find that out, I think. We need to define a workload. I think like blockchains are a good example. So there are estimations. I would have to look them up because they're a very particular use case. I would not really call it big data applications, but they really consume a lot of energy now. And the question is if that could not be optimized to achieve the same effect. I don't know, like a chain history of the coins that you want to create together with a safe mechanism to encode this that is actually cheaper in energy, right? Because that becomes an issue, right? Or the data centers that huge companies like Google also run, they are certainly consuming a lot of energy, but that is also like limited by what they pay for the energy in the end, right? If that would be out of the question or too expensive, they would change it, I suppose. Right? Well, oh my dear, I don't know the answer to that. I mean, it depends really on what kind of data you have, under which kind of policies it falls. So the GDPR, I believe, has to be keep data anonymized for 100 years or so. That's the general rule in the GDPR. If you want to work with personal data, it has to be more than 100 years old if you want to disclose anything. And then it really depends on the data sets, right? The next big anticipating breakthrough for big data. Yeah, if I knew that, I would probably not be sitting here. I don't know. I mean, the kind of analytics is going further, is going bigger, and then I think emerges more with these machine learning applications, so that we understand the data better, right? So big challenge always is semantic data, natural language processing, understanding natural language, for example. And you need a lot of data for that. You need a lot of text samples to analyze this, to translate the data among different languages and so on. So you need all these alignments which consume huge amounts of data. But then often it's also, for certain applications, it's limited by the amount of labeling that you can do. So most machine learning techniques, then if you go from big data to machine learning, combine them, need labeled data, training data for the algorithms. And then this also becomes a limiting factor, how to create so much training data, how to have good labels, and so on. But yeah, I think understanding the data that is available on the world, understanding images, autonomous driving, for which you need a lot of data, a lot of processing, a lot of samples that you see, these are major challenges. Yeah.
Okay, thank you very much. So I think that's the end of the session. So thank you again, Professor Theobald, for the very nice presentation. It was a pleasure to have you.
Yeah, my pleasure. Okay.
Okay, so then we'll see everyone again next week for the last session of our webinar series. Bye-bye.
Bye.